In this lecture, I'm going to take a look at two example problems involving vertical springs. For example, when I first of all demonstrated an oscillation to you, I did so vertically by hanging a spring from an attachment, because setting up a vertical oscillator is easy to do in the classroom. There are two forms of potential energy present in such a problem: spring potential energy and gravitational potential energy. So then therefore, how do we come up with an expression involving conservation of energy where we take into account those two forms of potential energy? Here's how we do so. Okay, so for vertical springs, we will look at two examples in just a few moments. We have two forces present, gravity and the spring force. So let's approach those two forces by using the work energy theorem. Okay, so recall, of course, the work energy theorem: net work equals change in kinetic energy. The left-hand side of the expression, however, is now the work done by two things, gravity and the spring force, when talking about a vertical spring situation. So let's write the left-hand side as the work done by gravity, plus then the work done by the spring force. Okay, and then recall that the work done by these forces is the negative of the work against. So this right here is the negative of the work against gravity. And this right here is the negative of the work against the spring force. And these work against terms are the changes in the different forms of potential energy. So then therefore we have change in gravitational potential energy, change in spring potential energy. And then if you take these two potential energy terms and move them to the other side of the expression, you then end up with the following. Here's our statement of conservation of energy when dealing with multiple forms of potential energy. Like so. This is how the conservation of energy equation always appears when you have additional forms of potential energy. You just have additional terms here, for example, to the right-hand side. So let's go ahead and employ this expression now for two simple examples. Okay, the first example is kind of like a version of the old toy that you may have played with when you were a small child called a jack-in-a-box. In a jack-in-a-box, you have a mass attached to a spring, and then ultimately the object moves upwards. We'll look at a variation of that in this first problem. Okay, let me go ahead and do some erasing here. And then let me read the problem to you here, and then ultimately you'll have to, of course, copy it down into your notes. Okay, let me move my file briefly. Okay, so this is a vertical spring problem where the mass is not attached to the spring. If it was attached to the spring, like in the jack-in-the-box toy, it's just another variation. Okay, a mass of 0.1 kilograms initially compresses a spring with a large spring constant, 500 newtons per meter. There's a large spring constant associated with the toy. Okay, we compress the spring a distance of 0.1 meters below the equilibrium position. The mass is released from rest, and then how high above the equilibrium position does the object rise to? Okay, so let's go ahead and approach the problem in the following manner. Okay, right here we'll say is the spring's equilibrium position. Here's the mass like so, and here's the spring. We're given that the mass is 0.1 kilograms. We're given that the spring constant K is 500 newtons per meter. And we're initially compressing the spring downwards like so from its equilibrium position, a displacement x that's given to us as 0.1 meter. And then we release the object from rest. The initial speed v0 is equal to 0. Okay, now we're going to do this problem entirely in one shot. It doesn't ask us, for example, to figure out what happens when the mass passes through the equilibrium position. If it did, it would just be another variation to the problem. Instead, all it's asking for is how high above the equilibrium position does the object rise to. So then therefore, I'm going to finish the problem up here with the object at rest for an instant. And then right here, we're going to call this distance above the equilibrium position h. And that's all the problem is asking us to find. It's to find h. So let's go ahead now and start filling in all the terms for our conservation of energy expression. When you approach the equation, you just go term by term, and you ignore everything else as you're working through the expression. So here's what I mean by that. Okay, first of all, the change in kinetic energy. Notice that the final kinetic energy is 0, and the initial kinetic energy is 0. So then therefore, the first term is 0 minus 0 for that reason. Write it as such in your notes. Write it as 0 minus 0, just so you understand later that the initial and final kinetic energies are both 0. The object starts at rest, and it ends up at rest. And now we have change in gravitational potential energy. Gravity has nothing to do with springs. So just ignore the spring completely and think of it like this. In terms of gravity, think of this right here as height 0. So then therefore the initial gravitational potential energy is at 0, and the final value then up here is mg multiplied by the total height of h plus x. I'm completely ignoring the spring when I describe this. So then therefore the final gravitational potential energy is mg times h plus x minus the initial, which is equal to 0. And now we get to the spring. Don't be fooled by the fact that the spring is vertical. We've already taken gravity into account. Now we just look at changes in spring potential energy. So the final spring potential energy is 0 because the mass is not attached to the spring. And incidentally, where is the spring at the end of this problem? Well, the spring is just like so, right here at its equilibrium position. It's not stretched or compressed at the end of the problem. Recall, of course, that the spring is idealized. It has no mass. It has no inertia. So then therefore, just think of it like this. The spring starts off as being compressed, and then it just instantaneously stops here at the equilibrium position as the mass continues upwards. So then therefore, it's not stretched or compressed at the end of the problem. Therefore, the final spring potential energy is 0. And then minus the initial spring potential energy, which just depends upon how far we're compressing the spring. A displacement x from equilibrium. So then therefore, the initial spring potential energy is 1/2 kx squared. So now we have changes in spring potential energy, final minus initial, like so. So you just go term by term and you basically ignore everything else as you're working. And now what I have to solve for here is h. So let's go ahead and move some terms around. Let's move this term here to the other side like so. And now this right here is the energy transformation that occurs, and very simply all that it says is that all the spring potential energy that we start with when initially compressing the spring is equal then to gravitational potential energy at the end of the problem. And now we just solve for h. Okay, so to solve for h, I got to do a little bit of math here on the right-hand side of the expression like so. And now I'll go ahead and subtract mgx to the other side and then divide by mg to get h by itself. Like so, after you do the math. And now let's see what happens when we plug in. What happened to my calculator? Hang on a second. I put my calculator on one of the other desks. Okay, so let's see what we have here. So in the first term in the numerator, 1/2 times 500 times 0.1 squared minus 0.1 times 9.8 times 0.1, and then all divided by 0.1 times 9.8. So after all of that, you end up with actually a pretty big height here. It's almost 10 feet. It's almost 2.5 meters, like so. If we were going to continue this problem into the future, then the object would just drop back down onto the spring and it would compress it once again 0.1 meters from the equilibrium position, and then basically it would just bounce up and down on the spring in this manner, rising always to this height here above the equilibrium position as each bounce occurs. Okay, now let's go ahead and take a look at our second problem. The second problem has to do with a demonstration that I showed you at the beginning of my lecture on Hooke's Law. Let's go ahead and revisit that demonstration. Before I do, however, I'll erase the board. You copy the problem down into your notes. It involves the hanging vertical spring. Okay, so let me erase this. Okay, copy the problem down into your notes involving the hanging vertical spring. And now I'm going to demonstrate it to you. I'm going to have to tilt my camera to do so, however. All right, so bear with me here as I tilt the camera. There we go. Okay, and then right here is my hanging vertical spring. Right here is the equilibrium position. And now I take my object here of mass m, and then I attach it to the spring like so. And then I let the spring hang down this displacement from the equilibrium position. This distance right here is referred to as x in the problem. Okay, and then secondly, I detach the mass from the spring. Let's go back up to equilibrium. And now I reattach the mass to the spring like so, but now I drop it from rest. And what I'm going to do is I'm going to catch it down at the bottom, like so. And then what we're asked to find is this distance here in relation to the original distance of x. So watch the demonstration again. So let's go back up to equilibrium. So right here, for example, like so. That right there is x. And now let's go back up to equilibrium and then drop. And then this right here is the distance that we want to find. What do you suppose is the relationship between the two? Let's see. Okay, so I'm going to tilt my camera back. Bear with me here as I do. Like so. Okay, and now here's our problem. Okay, so right here is the spring, like so, and right here is the equilibrium position. And then in the first situation, I attached the mass to the spring, and I just had it displace it like so, a distance x from the equilibrium position, and the object is just sitting here at rest. So then therefore, because the object is sitting there at rest, there's no energy transfer that occurs here. Instead, we have the forces acting on the mass canceling each other out. So let's describe that first. So I, of course, have the spring force upwards. Its magnitude is k times x. The weight downwards is mg, and then therefore mg is equal to k times x, like so. Okay, and then in the second scenario, I detached the mass from the spring, reattached it back up here at the equilibrium position, and then, as you saw, I dropped it. Okay, that situation looks like this. Okay, hang on one moment here. Okay, so now right here is my object of mass m, initial speed v naught equal to 0, and I'm dropping it from rest. And then the object ends up down here like so, with a final speed of 0 for an instant. Right here is the equilibrium position, and then right here is the displacement from equilibrium. I'm going to refer to that as h. That's the height change here in this problem, as well as the displacement from the equilibrium position. And now I'm going to go ahead and write off my conservation of energy expression. Like so. And now let's just go ahead and start to fill in the terms here, and let's see what happens. So first of all, the change in kinetic energy. Well, like in the last example, both the final and initial kinetic energies here are equal to 0. Okay, and then change in gravitational potential energy. Think of this right here as height 0. So the final gravitational potential energy is 0, and the initial then, therefore, when we're up here, is mgh. So final minus initial gravitational potential energy, like so. Okay, and now changes in spring potential energy. My final spring potential energy when I'm down here depends upon this displacement from the equilibrium position. So my final spring potential energy is going to be 1/2 kh squared, and then minus the initial value of 0, because we start at the equilibrium position. Like so. Okay, now if I clean up this expression a little bit, throw away the zeros and move this term here to the other side, you then just simply end up with this. mgh is equal to 1/2 kh squared. And then what I need to do is I need to relate together the values of h and x. Here's how I'm going to go about doing so. Right over here, I've got this force equation, and we have mg is equal to k times x. What I'm going to do is take this expression for mg and then plug it in right here into my energy transformation expression. So mgh, that's going to be kx times h equals 1/2 k h squared, and now we just solve for h. So I'm going to cancel out the k, like so, cancel out an h here and here, like so, and then if you solve for the remaining h, cross multiply the 2 to the other side, and h is equal to 2 times x. It's twice the original displacement from the equilibrium position, as you may have guessed when I demonstrated this a few minutes ago. Okay, so that concludes this short lecture on situations involving vertical springs.